Good morning and most welcome, dear students. Hope you all are doing good and prepared to begin with new academic year. Let us first seek God's blessings so that He may protect us and guide us throughout the year. Before we begin, I request you all to attentively watch the video and also keep your textbooks and a pencil handy with you during the class. The ones who do not have their textbooks can download the e-textbooks available online. Let us now begin with Science Part 1, Chapter number 1, Topic Gravitation. Let us first recall certain concepts which we have studied previous years. Types of the forces. We have studied about muscular force, nuclear force, electrostatic force of attraction, frictional force, and so on. Effects of force on an object. A force applied on an object can change the shape of an object. A force applied on a stationary object can even set it in motion. A force can also bring a moving object to the rest. Also, a force can change the speed and direction of a moving object. Gravitational force. We have already studied in our geography classes that gravitational force is a universal force which acts between any two objects on the earth as well as between the objects in the space. Before we study the concept of gravitational force, let us understand how the phenomenal discovery of gravitation was made. Sir Isaac Newton was the man behind the discovery. Concept of gravitation was discovered when Newton saw an apple falling from a tree on the ground. He wondered as to why the apple fell vertically downwards but not forming any other angle to the vertical or in the horizontal direction. He then came to the conclusion that the earth must be attracting the apple towards itself, and this attractive force must be directed towards the center of the earth. The direction of the apple on the tree to the center of the earth is vertical direction at the position of the apple, and thus the apple fell vertically downwards, that is perpendicular to the surface of the earth. As shown in the figure, the force acting on an apple on a tree is directed towards the center of the earth. Thus, he related the concept of gravitational force. He then correlated that if gravitational force exerted by the earth act on the objects very close to the surface of the earth, then the force could also act on an object at much greater heights and much far away from the earth's surface. For example, Moon. Moon is our only natural satellite which goes around the earth under the influence of gravitational force. Also, the planets, including our own planet Earth, also moves around the sun under the influence of gravitational force. Let us know some of the contributions made by the great scientist Sir Isaac Newton. He put forth the laws of motion, equations of motion, and theory of gravity in his book Principia. He mathematically derived Kepler's laws describing the motion of the planets. He also contributed significantly in the research work, including several areas such as light, heat, sound, and mathematics. He also invented a new branch of mathematics called calculus. He was the first scientist to construct reflecting telescope. In order to know more, kindly research through the online resources. Let us revise. A force is necessary to change the speed as well as the direction of the motion of an object. Try to recall Newton's 3 laws of motions which we have studied last year. Now think about, if earth can attract an apple, then why not the apple attract the earth towards itself? The earth is also attracted towards the apple by the same amount of the force as according to the Newton's third law of motion, which states every action has equal and opposite reaction. But we can't see it moving because force is proportional to the mass of the object as stated by F is equal to ma, and mass of the earth is very large in comparison to that of the apple. Therefore, force of the attraction by the earth is very large as compared to that of the force of the attraction by an apple, and therefore the apple gets pulled towards earth's surface but not the other way round. If moon is attracted by earth, then why does it not fall towards it? Now, motion of the moon around the earth is mainly due to the centripetal force. The centripetal force is provided by the force of the attraction of the earth. Due to the difference in the mass of the earth and moon considerably and centripetal force acting on them, the moon does not fall towards the earth's surface. Newton therefore cleared that the nature of the gravitational force is same whether it is on moon or earth, and earth attracts all the bodies towards itself. Gravitational force therefore acts between any two objects in the space or in the universe. In the next part, we are going to learn what is centripetal force. What is centripetal force? Let us do an activity. Tie a stone to one end of a string. Take the other end in your hand and rotate the string so that the stone moves along a circle as shown in the figure. Questions: are you applying any force on the stone? Answer: muscular force. This muscular force is being applied on the stone which is driven through the string. If yes, then in which direction this force is acting? As long as we are holding the string, we are pulling the stone towards us, that is, towards the center of the circle. How can this effect of force on the stone be stopped? Hence, what will happen to the stone? Answer: force stops once we release the string. The stone will thus fly off tangentially to the circle formed at the position of the stone when string is being released, because at that particular instance of time, that is its direction of velocity. Please watch this video.
Imagine you've got a tennis ball attached to a piece of string, and you start swinging it in circles. Whoa now, watch out for your buddy. Let's take a closer look at the fascinating physics of this simple action. You've probably heard of Newton's second law of motion as it relates to objects moving in a straight line. Turns out, Newton's second law also tells us about the net force on an object as it moves in a circle. When an object moves in a circle, its velocity changes direction. Since the velocity is changing, that means we have an acceleration. And we know from Newton's second law that if we have an acceleration, we have a net force. Now back to our spinning ball. For objects undergoing circular motion, the net force on the object is called the centripetal force. It's a weird-sounding word, but it's Latin for the phrase center seeking. It's named centripetal because the centripetal force always points to the center of the circle. The ball has a tangential velocity, so if you suddenly cut the string, it would fly off in whatever the tangential direction was at the moment you made the cut. But assuming you don't cut the string and you keep swinging the ball's tangential velocity is constantly changing directions. This means the ball is accelerating, and the reason it's accelerating is due to the centripetal force. The centripetal force acting on the ball is constantly directing the ball towards the center of the circle, your hand. This, combined with the ball's velocity, keeps the ball swinging in a circle. The same centripetal force that keeps the tennis ball swinging in a circle also keeps roller coasters on the track as they go through a loop-de-loop. So the next time you're having a blast on a roller coaster, you can thank the centripetal force.
Thus, any object moving in a circle experiences centripetal force which is directed towards the center of the circle. In order for an object to move in a circular motion around other object with a constant speed, there should be a force acted upon it which is directed towards the center of the circle, that is centripetal force. Let us define centripetal force. The force that acts on any object moving along a circle and is directed towards the center of the circle is called as the centripetal force. Let us remember certain terms. Centripetal force means center seeking or center attracting force. That is, object tries to move towards the center, whereas centrifugal force is just the opposite of centripetal force. That is, it is a center repelling or moving away from the center. Your object tries to move away from the center. Let us take an example, Moon, which is the only natural satellite of our Earth, which goes around the Earth in a definite orbit. During its motion around the Earth, the direction of the Moon as well as its speed changes continuously and constantly. Thus, centripetal force acts on Moon and is responsible for changing its motion and is directed towards the center of the Earth. Now imagine what would have happened if such force would have not been existed. In absence of such a force, motion of the Moon would have been in the straight line path, moving with a constant speed, and in certain instances of it would have been collapsed on the surface of the Earth. Thus, Earth tries to attract Moon towards itself by exerting centripetal force on it, which makes it revolve around the Earth. Similarly, the other planets in our solar system, including Earth, go around the Sun using the same phenomenon. I hope the concept of centripetal force is quite clear. Kepler's laws of planetary motion. Planetary motions were being studied by various astronomers since ancient times. Using the data available regarding the motion of the planets and their positions, an astronomer, Johannes Kepler, noticed that motion of the planet follows certain laws. Thus, he stated 3 laws describing planetary motions which were being known as Kepler's laws. Before we go to the laws, let us understand what is an ellipse. An ellipse is a curve obtained when a cone is being cut by an inclined plane, as shown in the figure number 1. It has 2 focal points as seen in the figure number 2, F1 and F2 as shown in the figure. The sum of the distances to the 2 focal points from every point on the curve is constant. As seen in figure number 2, A, B, C are 3 points on the ellipse, and F1 and F2 being the 2 focal points, AF1 plus AF2 is equal to BF1 plus BF2 is equal to CF1 plus CF2. Students, kindly watch the video.
Kepler's law of planetary motion. Kepler's first law. The orbits of the planets are ellipses with the Sun at one focus of the ellipse. There is no object at the other focus of the planet's orbit. The semi-major axis A of an orbit is the average distance between the planet and the Sun. As a planet travels in its elliptical orbit, its distance from the Sun and speed vary. A planet moves most rapidly when it is nearest the Sun or at perihelion. A planet moves most slowly when it is the farthest from the Sun or at aphelion. Kepler's second law. The line joining the planet to the Sun sweeps out equal areas in equal times as the planet travels around the ellipse. This is also known as the law of equal areas. Suppose a planet takes 1 day to travel from point A to B. During this day, an imaginary line from the Sun to the planet will sweep out an area. The same area will be swept every day. Here, the areas A1 and A2 are equal and the time T1 and T2 are also equal. Kepler's third law. The ratio of the squares of the revolutionary periods for two planets is equal to the ratio of the cubes of their semi-major axis. T square is directly proportional to r cube. So, T square by r cube is equal to Kepler's constant. Recapitulation. Kepler's law of planetary motion.
From the video, I hope all three Kepler's laws on planetary motions are quite clear. To review the video, you can visit through the YouTube channel. Of the three laws, the most important is Kepler's third law, which is being used for proving Newton's concept of gravitation. Kindly star mark these three laws and study them carefully. Students, kindly watch the video.
Newton's universal law of gravitation. All the above considerations, including Kepler's laws, led Newton to formulate his theory of universal gravity. According to this theory, every object in the universe attracts every other object with a definite force. This force is directly proportional to the product of the masses of the two objects and is inversely proportional to the square of the distance between them. The figure shows two objects with masses m1 and m2 kept at a distance d from each other. Mathematically, the gravitational force of attraction between these two bodies can be written as F proportional to m1 m2 upon d square, or F is equal to gm1 m2 upon d square. Equation 2. Here, g is the constant of proportionality and is called the universal gravitational constant. The above law means that if the mass of one object is doubled, the force between the two objects also doubles. Also, if the distance is doubled, the force decreases by a factor of 4. If the bodies are spherical, the direction of the force is always along the line joining the centers of the two bodies, and the distance between the centers is taken to be d. In case when the bodies are not spherical or have irregular shape, the direction of force is along the line joining their centers of mass, and d is taken to be the distance between the two centers of mass. From equation 2, it can be seen that the value of g is the gravitational force acting between two unit masses kept at a unit distance away from each other. Thus, in SI units, the value of g is equal to the gravitational force between two masses of 1 kg kept 1 meter apart. The center of mass of an object is the point inside or outside the object at which the total mass of the object can be assumed to be concentrated. The center of mass of a spherical object having uniform density is at its geometrical center. The center of mass of any object having uniform density is at its centroid. Use your brain power. Show that in SI units, the unit of g is Newton meter square per kilogram square. The value of g was first experimentally measured by Henry Cavendish. In SI units, its value is 6.673 into 10 raised to minus 11 Newton meter square per kilogram square.
From the video, we studied Newton's universal law of gravitation and its mathematical form. That is, F is equal to G m1 m2 upon d square. We shall be using this universal law in solving numericals in the next part. We have also studied through the video how the SI unit of gravitational constant was obtained. Thus, SI unit of G is equal to Newton meter square per kg square, and its value is estimated to be around 6.673 into 10 raised to minus 11 Newton meter square per kg square. Let us solve a numerical based on Newton's law of gravitation. Page number 15, exercise question number 5, sub-question F. The mass of the Earth and the Moon are 6 into 10 raised to 24 kg and 7.4 into 10 raised to 22 kg respectively. The distance between them is 3.84 into 10 raised to 5 km. Calculate the gravitational force of attraction between the two. The value of G is equal to 6.7 into 10 raised to minus 11 Newton meter square per kg square. Solution. Given mass of Earth m1 is equal to 6 into 10 raised to 24 kg, mass of the Moon m2 is equal to 7.4 into 10 raised to 22 kg. Distance between Earth and Moon r is equal to 3.84 into 10 raised to 5 km. Converting in SI unit, we get 3.8 into 10 raised to 8 meter. To find the gravitational force of attraction between the two. Solution. According to the Newton's universal law of gravitation, F is equal to G m1 m2 upon r square. Therefore, F is equal to 6.7 into 10 raised to minus 11 Newton meter square per kg square into 6 into 10 raised to 24 kg into 7.4 into 10 raised to 22 kg upon 3.8 into 10 raised to 8 meter the whole square, which is equal to 6.7 into 6 into 7.4 into 10 raised to 35 Newton upon 3.84 into 3.84 into 10 raised to 16. Therefore, F is equal to 2.017 into 10 raised to 20 Newton. Thus, gravitational force of attraction between the Earth and the Moon is 2.017 into 10 raised to 20 Newton, that is approximately 2 into 10 raised to 20 Newton. A small homework for you all students. Exercise page number 15, question number 5, sub-question number G. Similar to the one solved above, read carefully and try to solve. We have covered 3 topics in today's class. Kindly revise and study them carefully. Any doubts in any of the above topics can be cleared once we resume to our normal classes. Thank you for being patient and for your attentiveness. Best luck and see you all in the next class.